Download this code from codegive.com, link in the description below. Understanding memory connection to CPU, a deep dive. Connecting memory to the CPU is a fundamental aspect of computer architecture. It's how the CPU accesses and manipulates data. This tutorial will explore the key concepts, technologies, and code examples related to memory connection. We'll focus on the most common types of memory used in modern systems, DRAM, specifically DDR variants, and how they interface with the CPU. 1. Core concepts *****. Memory address space ****. The CPU sees memory as a contiguous array of byte-addressable locations. Each byte of memory has a unique numerical address. The size of the address space, example 32-bit or 64-bit, determines the maximum amount of memory the CPU can directly address. Memory controller ***. The memory controller is a critical component that resides on the CPU or northbridge, in older architectures. It manages all communication with the memory modules. It translates the CPU's memory requests, read/write operations, address, data, into signals that the memory modules can understand and responds with the requested data or confirms the data was written. Memory modules, DIMMs/SODIMMs. The physical memory chips are packaged into modules. DIMMs, dual inline memory modules, are common in desktop systems, while SODIMMs, small outline DIMMs, are used in laptops and other space-constrained devices. These modules contain multiple DRAM chips. DRAM, dynamic random access memory, the most common type of main memory. DRAM stores each bit of data as an electrical charge within a capacitor. The dynamic part means the charge leaks away over time, so the memory needs to be periodically refreshed. DDR, double data rate, a technology that improves memory bandwidth by transferring data on both the rising and falling edges of the clock signal. DDR2, DDR3, DDR4, and DDR5 are successive generations of DDR, each offering higher speeds, lower power consumption, and enhanced features. Memory bus the set of electrical connections, wires, that physically connect the CPU's memory controller to the memory modules. Key lines include address lines, data lines, control lines, read/write enable, chip select, clock, etc. Memory channels multiple independent data paths between the CPU and memory. Dual channel, triple channel, and quad-channel configurations increase memory bandwidth by allowing the CPU to access multiple memory modules simultaneously. Latency the delay between when the CPU requests data from memory and when the data is actually received. Latency is often specified using timings like CL, call latency, TRCD, RAS to CA delay, TRP, RAS pre-charge time, and TRAS, row active time. Lower latency generally translates to better performance. Bandwidth the rate at which data can be transferred between the CPU and memory, usually measured in bytes per second, GB/s. Higher bandwidth means the CPU can move more data in a given time, improving performance for memory-intensive tasks. Rank A rank refers to a set of DRAM chips on a memory module that can be accessed simultaneously. A single rank module can have all chips on one side. A dual rank module has chips on both sides, allowing for more memory capacity and slightly better performance in some cases. Cache memory a smaller, faster memory that sits between the CPU and main memory, DRAM. It stores frequently accessed data, reducing the need to access the slower main memory. Levels of cache exist: L1, fastest, smallest, L2, and L3, slowest, largest. Cache is crucial for performance. Virtual memory. A memory management technique that allows the operating system to use disk space as an extension of RAM. When the physical RAM is full, less frequently used data is swapped to disk. 2. Simplified memory access sequence. One CPU request *. The CPU needs to read or write data at a specific memory address. 2. Address translation. If applicable, the virtual address used by the program is translated to a physical address by the memory management unit, MMU. 3. Memory controller request *. The CPU's memory controller receives the physical address and command, read/write. 4. Signal transmission *. The memory controller sends signals, address, control signals, data if writing, over the memory bus to the memory modules. 5. Memory module access *. The appropriate memory chip within the module is activated based on the address. 6. Data transfer *. Read *. The memory module sends the data back to the memory controller. *. Write *. The memory module receives the data from the memory controller and stores it at the specified address. 7. Response to CPU *. The memory controller provides the requested data to the CPU, for a read, or confirms the completion of the write operation. 3. Memory technologies, DDR variants. Each DDR generation brings improvements in speed, power efficiency, and features. DDR2 * doubled the clock rate compared to DDR, improved signal integrity. DDR3 * further improvements in clock speed, reduced power consumption, introduced features like flyby topology. DDR4 * lower voltage, 1.2 V, higher density, introduced features like on-die termination, ODT, to improve signal quality. DDR5 * even lower voltage, 1.1 V, significantly increased bandwidth, introduced on-DIMM power management, PMIC, and ACC on-die, error correction code. Key differences *. Feature DDR2 DDR3 DDR4 DDR5 Operating voltage 1.8 V 1.5 V/1.35 V 1.2 V 1.1 V. Transfer rate lower higher significantly higher. Module pin count lower higher. Prefetch buffer 4-bit 8-bit 8-bit 16-bit. Architecture flyby independent subchannels. 4. Code examples, conceptual. It's important to understand that direct memory access in modern operating systems is usually managed by the OS kernel for security and stability reasons. User-level programs typically interact with memory through higher-level APIs, example malloc, new in C/C++, memory management in Python, Java, etc. Directly manipulating memory addresses requires special privileges and can lead to system crashes if done incorrectly. Example 1, low-level read/write, illustrative, requires kernel-level access. This example uses C and assumes you have the necessary permissions and hardware set up to access physical memory. This is not safe for general user-level applications. Important notes about the low-level example **. */dev/mem**. This is a character device in Linux that provides access to physical memory. It's usually only accessible to the root user or members of a specific group. *map*. The map system call maps a region of physical memory into the process's virtual address space. This allows you to access physical memory as if it were normal memory. *O_sync* ensures that write operations are flushed to memory immediately, not cached. Volatile the volatile keyword tells the compiler not to optimize away reads or writes to that memory location. This is essential when dealing with hardware, as the value at the memory location may change asynchronously. Address translation the physical address %map size calculation is crucial to get the correct offset within the mapped region. Security risks directly manipulating physical memory can have serious consequences if you write to the wrong addresses or corrupt critical system data. To compile and run, assuming you understand the risks. 1. Save the code as memory_access.c. 2. Compile gcc memory_access.co memory_access. 3. Run as root sudo /memory_access. Example 2, using malloc for dynamic memory allocation, standard approach. This is the standard, safe, and recommended way to work with memory in most applications. Explanation of malloc example *. 1. Malloc, size size of, int, malloc is a standard C library function for dynamic memory allocation. It requests a block of memory from the system's heap. Size of, int, calculates the total number of bytes needed to store size, which is 10 in this case, integers. Size of, int, returns the size of an integer in bytes, usually 4 bytes. 2. Error handling it's crucial to check if malloc returns null. Null indicates that the memory allocation failed, example not enough memory available. If allocation fails, you should handle the error gracefully, example print an error message and exit. 3. Casting the return value of malloc is void a generic pointer. You need to cast it to the appropriate pointer type, in this case, int before using it. For initialization and use you can then access and manipulate the memory pointed to by my_array as if it were a regular array. 5. Free my_array, this is essential. When you're finished using the memory allocated by malloc, you must free it using free. Failing to do so results in a memory leak, which can eventually cause your program to crash or the system to become unstable. 6. My_array equals null, after freeing the memory, it's good practice to set the pointer to null. This prevents you from accidentally using the freed memory, which could lead to undefined behavior. Example 3, C++ dynamic memory allocation, using new and delete. C++ provides new and delete operators for dynamic memory management, which are generally preferred over malloc and free because they provide type safety and can call constructors/destructors for objects. Key differences from malloc example new int size allocates memory for an array of size integers. New is type safe, it returns an int directly, so no casting is needed. Null use null instead of null in C++ 11 and later. Null is a type-safe null pointer constant. Delete my_array deallocates the memory allocated for the array. This is important because it tells the compiler that you're deleting an array. If you allocated memory for a single object, example int x equals new int, you would use delete x. Failing to use delete for arrays can lead to memory corruption. Example 4, Python, memory management is mostly automatic. Python uses automatic memory management, garbage collection. You rarely need to explicitly allocate or free memory. Explanation of Python example lists Python lists are dynamic arrays. You can add or remove elements as needed without worrying about explicit memory allocation. Garbage collection Python's garbage collector automatically reclaims memory that is no longer being used. You don't need to explicitly free or delete objects. Del keyword The del keyword removes a reference to an object. This can make the object eligible for garbage collection sooner if there are no other references to it. 5. Factors affecting memory performance Clock speed Higher clock speeds generally translate to higher bandwidth. Latency Lower latency results in faster access times, which can significantly improve performance. Bandwidth Higher bandwidth allows the CPU to transfer more data per unit of time. Memory channels More channels increase bandwidth. Memory rank Dual rank modules can sometimes offer slightly better performance than single rank modules. Cache size and speed A larger and faster cache can significantly reduce the need to access main memory. Memory controller efficiency The efficiency of the CPU's memory controller plays a crucial role in overall memory performance. 6. Troubleshooting memory issues Memory tests Tools like memtest 86+ can be used to diagnose memory problems. They run extensive tests to identify errors. BIOS/UEFI settings ensure that your memory is configured correctly in the BIOS/UEFI settings, example XMP profile enabled for rated speeds. Compatibility Make sure your memory modules are compatible with your motherboard and CPU. Refer to the motherboard's documentation for supported memory types and speeds. Overclocking Overclocking memory can sometimes lead to instability. If you're experiencing problems after overclocking, try running the memory at its default speeds. Physical installation Make sure the memory modules are properly installed in the DIMM slots. 7. Conclusion Understanding memory connection to the CPU is essential for optimizing system performance and troubleshooting memory-related issues. While low-level memory manipulation is generally handled by the operating system and hardware, understanding the underlying principles helps you make informed decisions about memory upgrades, BIOS settings, and application design. Always prioritize safe and managed memory allocation, using malloc, new, or the language's built-in mechanisms, unless you have a very specific reason to access memory directly and understand the risks involved. Modern operating systems and programming languages provide robust abstractions to handle memory management efficiently and safely.